Okay, just a couple of housekeeping notes before we get started. Please use the Q&A panel for any questions, comments, or concerns. The chat and raise hand feature are disabled. We will get you the slides and course resources after the course, as well as a recording of it. And I think that is it. And then Narayan, whenever you want to start, if you want to take a couple moments or whenever, you're good to go.
Okay, thank you, Brianna, for setting up this course. Thank you, everyone, for joining this course. Welcome to this course on error correction for quantum networks. I'm Narayanan Rangaswamy. I'm an assistant professor in the Department of Electrical and Computer Engineering here at the University of Arizona in Tucson. I work primarily on error correction for quantum computing, networking, communications, and sensing. And I have two wonderful co-instructors here, Michele and Suji. I'll let them introduce themselves.
Thank you, Narayanan. Hi, everyone. I'm Michele. I'm a student here, PhD candidate at the University of Arizona with Dr. Bane Vasic. And I work mainly on quantum LDPC code construction and also decoders for quantum LDPC codes, as well as entanglement distillation for communication. I will be talking about the first part of the course, which is an introduction to classical error correction. And I pass the ball to CJ.
Yeah, go ahead, Suji, introduce yourself.
All right. My name is Ye Cheng, and I'm a PhD student working with Professor Rangaswamy at the University of Arizona. I've worked on the repeater chain based on the distillation, based on the quantum error correction. And what I did, I will try to find a small code so far to increase the fidelity of the quantum network.
Thank you both for introducing yourself. So the course is broadly split into three parts. So the first part will be a brief introduction into classical error correction, where Michele will tell you all about the important concepts that we will then reuse when we introduce basics of quantum computing and quantum networking in the middle part, which I will teach. So after going through some introductions, then we will go into quantum error correction, and we will see how it relates to the classical error correction concepts that Michele introduces. In the final module, Suji will tell you about how to use this principle of quantum error correction to do this important task called entanglement distillation for quantum repeaters, which is very important and crucial for quantum networking. So that's the three parts of the course. We will have a lot of poll questions, as you might now be accustomed with other courses. So we will have frequent poll questions just to make sure that you're able to follow. Please use the Q&A to ask any questions. One of us will monitor the Q&A and answer your questions there. If it's important, we will bring it up and answer it live. Otherwise, we will answer it via text at the Q&A. It is also a good idea to have some scratch paper or some white sheets with you and pen and pencil, so that for poll questions, they will be quick ones, but you might have to do some small calculations. So it's good to have something next to you so that we can be engaged in the course. With that said, let's begin with the course itself. Go ahead, Michele, and share your screen, and let's get started with classical error correction.
Okay. So I will start with this slide. If you can read this sentence, and I guess so. I guess you're also able to understand the meaning of this sentence, which is obviously typing is no substitute for thinking. It is actually a quote from Richard Hamming. And what happened in this very time where you read this wrong sentence, and you reconstructed the information that was meant by it. It is exactly what we call error correction. And in fact, it happens on a daily basis in our brain, and we don't even know it. It is something very natural that we do every day with the language, and that we also apply to machines, to computers. And as you will see, computers will do exactly the same thing that we did here. So, but why were we able to correct the information of this sentence to basically to recollect it back? So we can define a set S. Let me use the laser pointer. We can define a set S to be the set of all the sounds that a human can produce. And then obviously a language is not more than a subset of it. A language is formed by words, and words together create sentences that we use to encode the information that we want to transmit into code words. And then obviously we have a huge complementary set, which is S minus L. It is the set of the sounds not belonging to the language. So because the language is a subset of S, then we're able to basically assign each element in this set S minus L to an element of L, as it will be much clearer later. But essentially, the words that we have on the left, they belong to S minus L. So they are sounds, or in this case, I should talk more about sentences that we can write or words that we can write that don't belong to any word. They are not word of the language. And then what we do, we apply the maximum likelihood decoding that we will formalize later to map them back to code words or words of our language. Okay, so of course, computers, they don't talk English. They speak the binary language, so they talk using zeros and one. And so we will define all our operations over the binary field, which we indicate with this notation F2n. 2 indicates the binary nature of the field, so we only have 0 and 1, and n is the length of each vector. So we have binary vectors of length n. And operations between these vectors or between binary numbers are defined by these two tables. But I guess most of you are already familiar with this. And we also assume that each word of our language is independent from the other. This is not quite the case for the human language, where the words are correlated, but it will be sufficient for our analysis to consider each word to be independent. In this case, we will talk about block codes. And so we basically redo what we did before with the human language. We take the space of all the binary vectors of length n, which is each vector is represented as a white dot in this set. And then we take a subset of it. For instance, we can, in principle, we can arbitrarily define it to be this set of blue dots. And now we just say that these words, they belong to our code. And all the other remaining white dots, they don't belong to our code. So because we are talking about linear codes, we will have 2 to the k vectors, because these 2 to the k vectors will be generated by a set of k generators. But in principle, this can be any number. So we have a set of vectors that we define to belong to our code C, and all the others won't belong to our code C. So let's see it with an example, a very simple example, which is called the repetition code. In this case, the 313 repetition code. So instinctively, what do you do when you want to, tell someone something, but there is a lot of noise? So the most primitive thing that you can do is to repeat the same thing multiple times. And this is exactly exactly what happens in the repetition code, as we will see. But first, let me introduce this notation that we're using here, 313, in this case, stand for NKD in the general case, where N is the length of our code words. K is what we call the code dimension, which is the amount of logical information that the code can encode, and as this will become more clear later. And D is the minimum distance in the Hamming sense. Let me introduce you the concept of minimum distance in a moment. So in the repetition code, K is equal to 1 because we can only encode one bit. This bit is either 0 or 1. And therefore, we will have two code words, the code word corresponding to the 0 bit and the code word corresponding to the 1 bit. As you can see, it is quite simple. The repetition code simply means repeating the bit that we want to transmit for a certain number of times, in this case, 3. So we only have the all0 code word and the all1 code word. The Hamming distance between the code words is the number of positions in which they differ. So in this case, the minimum distance between these two vectors is 3, because in all the 3 positions, we have 2 different entries. And of course, we can, when we have a code with many code words, we will compute, in principle, we can compute the Hamming distance between each code word. And then this parameter D is the minimum of those distances. Why is the minimum distance that we care about? It will be clear, more clear later, but essentially the minimum of these Hamming distances defines how much our code can correct, how many errors we can correct. And we can see the repetition code as a reorganization of the binary field of vectors of length 3, which has 8 elements, which are all depicted here. As we can see it as reorganizing our space into 2 balls or spheres, 2 Hamming spheres. Each sphere has as center a code word, and the other elements inside the sphere are elements that are not belong to the code, but that are at minimum Hamming distance from these code words. So for instance, we analyze now the ball of 0, 0, 0, and we have these 3 code words, these 3 vectors that are not code word, but they are at Hamming distance 1 from 0, 0, 0, and Hamming distance 2 from 1, 1, 1. And so they belong to the 0, 0, 0 ball. And similarly, these vectors here, they are distance 1 with the 1, 1, 1 code word, and distance 2 from the 0, 0, 0 code word. And so they belong to the 1, 1, 1 sphere. And so the number of correctable errors is denoted with this bracket notation, which means floor. So basically, we take the smallest integer, we round down basically the result of this division. And again, this relation will be clear later, again, when we will see the examples. But for instance, for a distance 3 code, you can see that T is equal to 1. So we can only hope to correct 1 error. We also define the code rate, which is simply K over N, which gives us the amount of redundancy that our code adds to protect our information. So if R is close to 1, then the code rate is high, and we don't use a lot of additional bits to protect the information. On the other hand, if R goes to 0, then we add a lot of redundancy. And the repetition code is generally a code with very low rate, as you can think of. We can repeat this. We can repeat the bit how many times we want, and the more bits, the more redundancy we introduce, and the lower the rate will be. But also, we will be able to correct more errors. Okay, so we have the first poll question. So how many redundancy bits are used in a 155.10.21 code, and how many errors are guaranteed to be corrected, and how many code words does the code have? So you guys will enjoy answering this first polls. I'll give you some time. So, is the poll closed? I'm not sure if I'm able to see the answers. Okay, thank you. Okay, so I see the distribution is quite uniform. So the correct answer was A. So we have 145 redundancy bits. You simply do 155 minus 10. 10 is the bit of informations that we have, and 155 is the length of a code word. So we introduce 145 more redundancy bits. The minimum distance is 21. So if you compute floor of 21 minus 1 by 2, it gives you 10. And we have 1024 code words because it's 2 to the power of 10. Okay. So if we want to correct errors, we need to understand how these errors are introduced by the channel. And for our analysis, we will simply use this model, which is called binary symmetric channel, where each bit is flipped independently with probability alpha. So you see here that we have bit 0 has a probability alpha of transitioning to 1 and a probability 1 minus alpha of remaining 0, and so is for the bit 1. And so from here you can see that the most likely error is the one with the smallest number of flips. So for instance, weight 1 error, for instance, where I say weight 1, referring to errors where we only have one flip, has probability alpha times 1 minus alpha squared, because we have one flip and two non-flips. And this is bigger than having 3 flips, which is alpha cubed, and also bigger of having 2 flips. So you can see in the binary symmetric channel, the error that will happen the most is the one with the smallest number of flips. And this will be important in the following. So now we want to do the maximum likelihood decoding exactly how we did before with the sentence that I put in the screen. So assume that we have a code word, the 0 code word, 000, and we send it through the channel, binary symmetric channel, and say the channel introduces one error in the central bit. And now you can see that we will be able to decode it using maximum likelihood decoding. What we do is simply locate the received vector y in one of the Hamming spheres. So we see that, as we've seen before, 010 is in the hemisphere of 000, so it is at distance 1 from this code word and at distance 2 from this other code word. And since we know that the channel is most prone to introduce one flip than two flips, then we see, well, the most likely code word to be transmitted is the 00 code word, because it's more likely that the channel introduced one error than two. So now assume that we transmit the 00 code word and the channel introduces two errors and we receive the sequence 110. What is the output of the maximum likelihood decoder? Maybe I shouldn't share uh, the answers might influence you, but okay, so the majority of you answered correctly. The answer is C. And this is what happens. The channel introduces two errors, but the vector 110 belongs to the ball of 111, and therefore the decoder says, okay, it's the most likely error that the channel introduced is a weight 1 error on the third bit. So what actually the maximum likelihood decoder does is, in this case, it introduces more error on top of the errors introduced by the channel. So you can see that there's nothing better than we can do here. And the reason is that the 3-bit repetition code can only correct one error because it has minimum distance 3. And as soon as we have two errors, then the maximum likelihood decoder cannot correct errors anymore. And there's nothing, again, that we can do on other than increasing the minimum distance of the code. So now we will formalize a little bit better the concept of maximum likelihood decoding. Here, you can visualize the space of all the binary vectors of length n. And with the orange dots, I depicted the code words. The white dots are all the other vectors not belonging to the code. And these lines that separate the regions, which are called decision regions or Voronoi regions, those are simply the Hamming balls corresponding to each code word. And then the maximum likelihood decoding is simply saying, okay, I received this vector here, for instance, then the most likely code word that was transmitted was this one, belonging to this ball. And now we will see that doing maximum likelihood decoding over the binary symmetric channel, it is equivalent actually to doing minimum distance decoding, which is basically what we did before. As I said before, it is the most likely error is the one with smallest weight in the binary symmetric channel, and we will now prove this. So assume D is the Hamming distance between two vectors x and y. For the binary symmetric channel, we know the conditional probability of y given x, when x is the transmitted code word and y is the received vector. And it is basically the probability. Sorry, actually, x and y are two arbitrary binary vectors, the conditional probability, assuming that X was transmitted to the channel and Y was received, is the probability of having alpha flips. Sorry, D flips, where D is the Hamming distance between X and Y. So we have D flips. Each flip happens with probability alpha, and so this is the conditional probability. Now, X hat is the code word that is, the most likely code word that was transmitted. And it is the one that maximizes this probability, probability of X given Y. So given the received vector that I received, what is the most likely code word that was transmitted? Now we can use the Bayes rule to write it in this form, but now we see that assuming that all the code words are equally likely, this P of X is a constant. And also P of Y doesn't depend on X. So this is equivalent to maximizing just P of Y given X. And in this case, we will maximize the logarithm of that because it is equivalent, but it is handy because we can use the log rules to put down the exponents. So now the logarithm of this becomes this thing here where we have this exponent D now multiplies log 2 of alpha, and this exponent n minus D multiplies log 2 of 1 minus alpha. And now we can rewrite this, and we see that the only term that depends on X here is the first term, because D is the Hamming distance between X and Y and depend on X. So this is constant over X. And so the maximizing this, it is equivalent of minimizing D because this term is negative, this logarithm. And so minimizing D, it actually means that we choose X to minimize the Hamming distance with Y. And this will be the code word that the most likely transmitted code word. So basically, it is, again, just a formalization of what we just did with the examples that we've seen before. I received some vector, which is the code word with minimum Hamming distance from that vector. That is the most likely code word. Okay, so these were the basic ideas of what is a code, what is a decoder. And now we will move forward to other concepts which are still very important. The first one is matrix representation of codes. So since we are dealing with linear codes that are basically linear subspaces of the binary field, these spaces can be represented with matrices. And we have two matrices that represent a code, the same code. One is the generator matrix. So a generator matrix G is a matrix such that given a binary vector of length K, which we call U times G gives you a code word of the code G. So G is basically a set, so is a matrix where each row is generating element of the code. A code word is a code word that generates all the other code words. On the other hand, H is the parity check matrix of the code, which is defined in this way. Given X to be a code word of the code, then it must be that X times H transpose gives you 0. So in other words, the code space is the kernel or the null space of the parity check matrix, and the image or the row space of the generator matrix G. And since G, each row of G is a code word itself, then obviously G also belongs to the null space of H. And we use these two matrices to represent our code. Especially the parity check matrix is very important for low density parity check codes, as we will see later. So for example, we can see the parity check matrices and the generator parity check matrix and the generator matrix of the 313 repetition code. So the code words of the repetition code are either 000 or 111, and therefore the generator matrix is simply 111. If you multiply it by 0, you get 000. If you multiply by 1, you get 111. In general, the generator matrix has k rows and n columns. And the parity check matrix instead looks like this. It has n minus k rows and n columns. And you can try yourself to multiply a code word, the 111, for instance, code word by H transposed, and you get a 0 vector. What happens when you multiply something that is not a code word for the parity check matrix? So assume that you have a code word X, and you have some flips that your binary symmetric channel introduces. You can model it as a summation of your code word plus some error vector. Then you multiply Y by H transposed. But Y is equal to X plus C. And this addition, again, is always over the binary field. So now you can use the associative property and separate these two terms. But obviously, the first one, by definition, is equal to 0 because X is in the kernel of H. Therefore, what you get at the end is what we call the error syndrome. That only depends on the error vector that the channel introduces. So now how we can use the syndrome, actually, we can use the syndrome to recover the error that happened. Let's see with this example. Assume that we transmit the O0 code word, and we have a flip on the first bit introduced by the channel. Now we multiply Y by H transposed, and we get this syndrome, 1, 0. Now we can use what we call the standard array table. So let's go through this table. The first row, in the first row, we can see the code words 0, 0, and 1, 1, 1. And in the leftmost, or I should say rightmost columns, you have the rightmost column, you have all the possible syndromes. So H in this case has 2 rows, so we have 4 possible syndrome values. And here, in the central part of the table, you have all the possible error vectors that can happen. And so what you do when you have this syndrome here, you locate it in the table, and then you go to the leftmost element corresponding to the row of this syndrome, which in this case is 1, 0, 0. And so we now, and we actually decoded the error. So we now know that given this syndrome, then this is the most likely error because we constructed the table in such way. If we had some other syndrome, then obviously the most likely error is always the one in the leftmost part. And so this table actually implement maximum likelihood decoding. However, assuming that we have some other code, a 743 Hamming code, where these are the generator and the parity check matrix, and k is equal to 4, so we have 16 code words. So now the standard array table looks like this. And you can see that it is much bigger than the other. We did not increase the length of the code or the dimension of the code a lot. But the size of the table, number of rows and columns, it increased a lot. And therefore, this standard array decoding method is not practical. Because imagine that you want to write a simple algorithm that, given a syndrome, looks for the, given a syndrome or a received vector, looks for the most likely error. You have to implement an algorithm that looks over all a table, and this will take, an average number of times of time equal to the number of roughly of columns and rows. And if this number of columns and rows grows exponentially with the length of your code, then your decoder will become slower and slower. And if you use, say, a length 100 or 200 code, then your algorithm is too slow to have any practical interest. Decoder should be fast. And therefore, this method, although is the best that we can do in theory, it's not very desirable. So another poor question. Assume that you're using this 743 Hamming code. You receive this vector here. And you also measure this syndrome here. So I forgot to mention before that we can also use the table in the other way around. So given this received vector, 1, 0, 0, we can now also find the most likely transmitted code word, which is so we take the syndrome, we look to the leftmost element, which is the most likely error. The most likely code word is the one on top of that column. So, but anyways, getting back to the poll, we receive this sequence and we compute the syndrome. What is the most likely transmitted code word and the most likely error? So now I hope you guys can see the table and use it. So maybe I can put the bigger version. Okay. So maybe take note of the transmitted sequence here that you can see 110, 1110, and the syndrome 011. And are you able to use the standard array table to find the most likely error and the most likely transmitted code word? So remember, you get your syndrome, you locate it in the final column here, and then you go through the row corresponding to that syndrome, and you find the most likely error, and then you find the code word. So the majority of you answered D, which is actually the correct answer. So we get the syndrome 0 and 1, we locate the corresponding row, And then we locate the received vector here in this row, which is here. And then the most likely code word is the top element in that column. So good job, guys. You now know how to do the maximum standard array table decoding. So before moving to LDPC codes, let me introduce the concept of dual codes, which will be important in quantum error correction. So we have seen that a repetition code can be represented using a generator matrix and a party check matrix. But now, what happens now if I say, okay, now I want to define a code where this is my generator matrix? What will happen is that it automatically, this will be the party check matrix. And what we obtain is what we call the dual code of the repetition code, which is called single party check code. So the dimension of the dual code will be n minus k of the previous code. So n minus k is equal to 2 here because it's 3 minus 1. And so k in the dual code will be 2. For the minimum distance in general, there is no defined rule. It can be any, in principle. And then this property holds, obviously. The rows of the parity check matrix of 1 are in the kernel of the parity check matrix of the other one. And therefore, you have this notion of dual codes, which basically means the kernel of one is generated by the other and vice versa. I won't go deeper in this, but this was just nice to introduce because it will be important later. Actually, this property, you will see it's important for quantum extraction. And now we introduce finally low density parity check codes. So LDPC codes were considered because of they allow sparse parity check matrices. So what does it mean sparse? It means that basically they have a lot of zeros and just a few ones. This is it is just that definition of a sparse matrix. And a sparse matrix is of interest because it allows low complexity decoding algorithms. So you recall how this standard array decoding was exponentially complex and it was not interesting from practical purposes. So for LDPC codes, we can use other algorithms that are suboptimal in the sense that they do not achieve maximum likelihood. To be clear, some errors that the maximum likelihood decoder could correct, these decoders will fail to correct. But nonetheless, those are very simple, very low complexity decoders, and in practice, these are the state of art in coding theory. And so, because low density parity check matrices, low density parity check codes have sparse parity check matrices, they allow low complexity decoding algorithms that operate on these matrices. And in practice, these matrices will be seen as graphs that I will now introduce. The Tanner graph by its creator, Michael Tanner. So recall the parity check matrix of the repetition code. We now define each column to be a node of our graph, of a Tanner graph. We call a variable node. And each row of the matrix is another type of node, which we call a check node. It is a bipartite graph, so we will have the set of variable nodes and the set of check nodes. These nodes are connected to an edge if there is a 1 in the corresponding entry of the matrix. So we have the set of variable nodes, the set of check nodes, And the variable node j and the check node I are connected with, through an edge if the ij element of the parity check matrix is equal to 1. And so we can visualize the tunnel graph of the repetition code with in this fashion. So V1 is connected to only C1, V2 is connected to both, and V3 is connected only to C2. And it is bipartite graph, which means that variable nodes are not connected between each other, and also check nodes are not connected between each other. And this is a more realistic example of the tunnel graph of a parity check of an LDPC code. It doesn't tell much if you look at this in this way, but it just, I don't know. I just thought it was nice to see how a real tunnel graph looks like. In this case, we can see that each variable node is connected to exactly 3 edges. And similarly, each check node is connected to 5 edges. So this is what we call a regular code, where dv is the variable node degree and is the number of edges incident to each variable node. And dc is the check node degree, so the number of edges connected to each check node. And we denote with this calligraphic n the neighborhood of each node. Regular codes are important, especially for if you want to analyze your decoder, assuming that each node has a constant number of edges. It is very handy. But there are also codes where each node is connected to, has a different degree and they have different properties. But this is a bit too technical now, and it's not of our interest. So given this tunnel graph that you see, are you able to reconstruct the corresponding parity check matrix? Okay, great. Most of you answered B, which is the correct answer. So the first variable node is connected to check 1 and check 2. And you see the first column has a 1 in the first and check 1 and check 3. So we have a 1 in the first and the third rows. Similarly for check node 2. So these two columns will be the same. variable node 3 is connected to check node 1 and check node 2, and so on. We have another poll question to keep you focused. So given this standard graph, one of the following statements is false. We have n equal 25 and dc equal 5. The check degree is 3, n equal 25, and the standard graph is bipartite, and it's a regular LDPC code. One of these is false. So while you answer to the poll, I will take advantage of this occasion to switch from my iPad as my battery is running low. So I will stop sharing for a moment, and we will see the answers just in a couple of seconds. Okay, let me now share my screen again. Okay. Okay, great. And so most of you answered correctly. Okay, so we can move on. And we can now talk about iterative decoding. So we will see actually an example of these low complexity decoders that I've talked about and I mentioned before that operate on this standard graph. So as I said, these are low complexity algorithms. They operate on the Tanner graph. And in each iterations, we have messages exchanged by variable nodes and check nodes. And we have a early stopping criterion, which is if we match the syndrome that we have measured, then it means that we have recovered and collected the error. Or if we reach to a non-zero syndrome, it means that we have recovered the correct code word. And so we succeeded. Otherwise, we continue for another iteration. And in each iteration, there is an exchange of messages between variable and check nodes. So we will see a simple algorithm, which is called the bit flipping. It is very simple, but it is also, I have to say, of practical interest in many fields. So in the bit flipping algorithm, we have an initialization of the messages. So with new, we indicate the variable to check message, and the message that the jth variable node sends to the ith check node is simply the jth position of the received vector.
So if that entry of our received vector is 1, you will send a 1 to all the neighboring check nodes, otherwise you will send a 0. With mu, we indicate the check to variable message. And a check node sends to all its neighboring variable nodes the binary summation of all the received messages from the neighboring variable nodes. And then in the following iterations, each variable node simply compares the summation of the received messages from the check nodes with some threshold beta. And if we have the summation of the messages is bigger than beta, we flip the message, which this flip is represented by this summation with 1. Otherwise, we leave it like it is. So I understand that it might seem quite complicated by looking at the formulas. So I guess it would be much more clear with an example. So now we see. Before we have another poll question. So what is the check to variable message of a bit flipping decoder computed at the check node? So remember that a check node computes the summation, the binary summation of all the incoming messages. And so obviously the result of the binary summation would be 1 if you have an odd number of 1 and 0 if you have an even number of zeros, right? Okay, so maybe we wait a little bit more. Okay, so most of you answered B, which is the correct answer. And now we have another poll question. What is now the message computed by this variable node, considering the incoming messages? So here we assume beta equal to 1, and the previous message, the previous variable to check message, is also 1. And now, as I've said before, we compute the summation of all the incoming messages from the check, and we compare it with beta. And then we decide, based on this comparison, whether we flip the message or not. So I think we can move on a little bit faster now. The answer is 0. And the reason is that the summation of the incoming messages is 0 plus 1 plus 1, which is 2. 2 is obviously bigger than beta, which is 1. The previous message was 1. Therefore, we flip it and we send a 0. So now let's see a more concrete example of bit flipping, considering this parity check matrix that I have designed specifically for this example. And the tunnel graph will look like this. And assume that we receive y as a received vector. Now in the first iteration, we have that each check node computes, as we've seen before, the binary summation of the variable nodes where it is involved. So for instance, we can see that this first check is connected to these 3 variable nodes. And so we have 1 plus 0 plus 1, which is 0. And similarly, the second check is connected to this variable node, this one, and this one. So we have 0 plus 1 plus 0. And so we have 1 here. So we do this for all the check nodes. Now we compute the incoming messages from the checks for all the variable nodes. So for this variable node, we have the connection with this check and this other check. So we have 1 plus 1, and here we have 2. Similarly, for this 1 and 1, we have 2 as well, and so on for the others. Now recall that we compared this sum with a threshold, beta, which in our case, we set to 1. And therefore, we have that all the variable nodes which with value 2 will be flipped. And the others will remain untouched. I have highlighted in red the flipped variable nodes. As you can see, if it was 0, now it's 1, and if it was 1, now it's 0. And now again, this was one iteration of this flipping, and we proceed with the second one. In the second one, each check computes again the messages, and we have these values for the checks. And now we do the same as before for the variable nodes, and you will see that the only variable node connected to 2 checks with value 1 is this. And so this will be the one that we flipped. And now you see that in the third iteration, we compute the values from the checks, and all these values are 0. So this means that this is a valid code word of the code, and therefore we stop decoding, and hopefully we have estimated the right code word. So as we're running short of time, I will not spend too much in belief propagation, but I just wanted to introduce it to you guys because it's very important. It's a very important algorithm. It is, again, a message passing decoder, a message passing iterative decoder, and it has a beautiful mathematical derivation where basically the goal is to estimate the most likely value of each bit. So we basically, again, we use the maximum likelihood decoding rule, but now for the single bit, and we use the marginalization. And now assuming that our tunnel graph is a tree, we can do some mathematical manipulation, and we can see that the estimate for x1 can be represented as a product of summations of probabilities. And this is why the algorithm is called sum product. And by using this fact, we design our variable to check and check to variable messages to iteratively update these probabilities and eventually converge to the estimate for each bit. If the Tanner graph is a tree, this will be equivalent to maximum likelihood decoding, but unfortunately, Tanner graphs are not tree, and therefore belief propagation or some product in LDPC codes is suboptimal, but nonetheless, it is still an excellent algorithm. So now, before finishing my section, I want to just briefly introduce the concept of Monte Carlo simulation. So Monte Carlo simulation is very important in many areas of science. In error correction, we use it to estimate the performance of a code and a decoder over some channel when we cannot run, we cannot analyze it mathematically. So basically what we do, we simulate the transmission of many code words, and we simulate the channel, and we use the decoder to correct the errors introduced by the simulated channel, and we can see whether we have succeeded or failed in the decoding. So we have actually a random sampling of the errors introduced by the channel. And obviously we need these simulations to be fast. So, okay. So how do you run a Monte Carlo simulation for error correction? You choose an error model, for instance, the binary symmetric channel. Then you choose a code and a decoder that you want to benchmark the performance under that channel. You fix a large enough number of samples. You fix the parameters of the channel, for instance, the alpha parameter, which is the probability of error for the binary symmetric channel. And then for each sample, you generate a code word randomly. You generate a random sample of noise. You compute the syndrome, and then you start decoding using, for instance, bit flipping or belief propagation. If the decoder fails, you count a failure. And then the probability of error of your code and your decoder will be just the number of failures divided by the total number of samples. And then you repeat this for these different parameters of the error model. So for these different probabilities of error. The result will look somehow like this, where here on the x-axis, actually, it's not illustrated, but we have, it is not the alpha parameter of the binary symmetric channel. It is some other channel, but it is not important. And here on the y-axis, we have the probability of error of a code and a decoder, and we have different codes. So for instance, we have an irregular LDPC code, which performs very well. As you can see, it drops almost vertically. We have a turbo code and so on. We also have another plot here. Here we can see the simulation result for a binary symmetric channel. So on the x-axis now we have the probability of flip, and we have the error rate on the y-axis, and you can see that it decreases. We have two different decoders here. We are not interested in the details now, but now you can see that you can distinguish two errors. One is this region here, which we call waterfall, and you can see by here decreasing slightly the probability of error of the channel. It actually makes the failure rate of the decoder to drop as well with some slope. But then it happens, so this is the waterfall region, while here you can see that the slope changes, and for a small enough probability of error, and this is what we call error flow region. And we will not dig into the detail of this, but the purpose was just to show an example of how decoding simulation looks like and how to perform it. I hope to have been clear enough. And so with this, I now leave the stage to Professor Rangaswamy for the core part of the course. And thank you for your attention.
Thank you, Michael, for the great introduction to classical error correction. So hope everyone got the basic ideas. I think for most of the poll questions, I was very happy to see that that you got the answers correct. So maybe let's take a few minutes break. Let's maybe resume in another 5 minutes. Stress yourself and try to recall all the main concepts that Michele introduced. What is a code? What is N, K, and D? What is minimum distance? What are errors? How does a decoder work, and so on. And then we'll come back in 5 minutes and start with the quantum error correction. We wait for 1 more minute and then we'll start. Yeah, thank you for all the questions in the Q&A. So if you have more questions, keep asking there. One of us will answer it, and if necessary, we'll also answer it live. Okay, let's continue with the course. So far, Michele introduced all the basic concepts of error correction. So in a nutshell, if you want to think of it intuitively, the way you can think of it is that if you have, say, a single bit, and if errors happen, then you have no way of knowing that something wrong happened, right? So if you just transmit raw data over the channel, and if some bits get flipped over the BSC, and if you had no protection, then there's no way you can learn about the errors. Whereas if you encode the bit into a code word, where it's now somehow correlated with all these bits, you're adding redundancy in a controlled way. And then if one of these bits goes through an error, then you have many correlations between this bit and others. So you can perform these checks to figure out what happened. Even though you might not know exactly what the value of that bit is, you can actually check for errors and still correct them. So it's kind of like saying united we stand, divided we fall. Now here is a plot of one of the famous codes in quantum error correction called the surface code. So I'm showing this up front just to show that you can also visualize these error rate plots that Michele showed you in a different way. So here what we are plotting is some kind of physical error rate similar to the alpha parameter for the BSC. And then in the y-axis, instead of the probability of error, we are plotting what's called the time to failure. So this is kind of like saying this is the average time for which the encoded information is alive, and it's without errors. And you see that we are plotting this for different code distances from 3, 5, all the way up to 11. And so as you increase the code distance, you expect things to get better, but that depends on which regime of the physical error rate you are in. So there is this critical point here where all these curves meet. So this is called the threshold for this family of codes. The family is characterized by some properties, and you keep increasing the distance. So each member of the family has a particular distance. And so this is the kind of inflection point. So to the left, what happens is as you increase the distance of the codes, the time to failure increases, which means you're preserving the information for longer. Whereas to the other side of the threshold, if you increase the distance, you're actually getting worse and worse. So this is a very critical point. It's a phase transition where things go from worse to better as you increase the size of the code or increase the distance of the codes. So we'll get to this, but this is a picture that's good to have in the back of your mind. Okay, so where do we start? So in quantum computing or quantum networking, you're trying to preserve information. So just like we did for classical bits, you can take qubits, say k qubits of information, and you can encode it into n qubits, where n is larger than k. But you're not only just encoding and preserving information, you need to process it. You need to compute on it, or you need to do some quantum networking protocols, and so on. So all of these physical operations happen on the encoded information, and these need to be fault tolerant. Fault tolerant means that errors in some places don't catastrophically spread and completely overwhelm the system. So there's a more precise definition, but we won't get into that. So you encode information, and then you have to physically process them, and finally you decode, and hopefully you get to the same end result that you would have got if all your original operations were noiseless. So you wanted to do some processing on the information you had, but these logical operations are noisy if you implement it in the lab, which is why you encoded and try to do things fault tolerantly so that the code can help you correct some errors. Now, when you encode and do this processing, you have to also guarantee that any logical operation on this logical qubits can actually be performed by physical operations on the physical qubits. And in quantum information, it turns out that you can do arbitrary computation if you can do these three logic gates. This is called the Hadamard, this is called the T gate, and this is called the control NOT, or it's also the reversible XOR. So we won't get too much into the definitions of these gates for this course, but it's good to have in the back of your mind that using these three operations, you can actually do arbitrary quantum computation. Okay, so that's the basics. So overall in quantum error correction, you need to correct errors, but you also need to do logic. You need to perform computation on the encoded information. Now let's start with the basic quantum gates. The first is called the bit flip gate, which if you take the computational basis states, this is denoted as ket0. This is called ket1, K-E-T. So these are all vectors in complex vector spaces, but we won't get into that vector space definition for this course as it's not necessary. So for now, just take these as definitions of some basis states in a linear algebraic sense. And so this X gate flips 0 to 1 and 1 to 0. And this can be visualized on the so-called block sphere, where I've plotted 0 and 1, these basis states, and X is basically a rotation about this axis where 0 becomes 1 and 1 becomes 0. Similarly, there's a phase flip gate, which what it does, it rotates about the z-axis. So if you acted on 0 and 1, it would do nothing to 0, but it would introduce a phase of -1 if you acted on 1. Now you can rotate the 0, 1 basis to the so-called plus-minus basis. This is just a 45-degree rotation in the 2D plane. And then what happens is Z actually performs a bit flip on the plus-minus basis, whereas X does a bit flip in the 0, 1 basis. And then there's the Y, which is a combination of X and Z, where it's a rotation about the Y-axis. And this is how it acts on the basis states. On 0, it flips to 1, but also introduces a phase I. 1, it flips to 0 and introduces a phase -I. So these are the basic quantum gates. And once you have these basic quantum gates, you can actually define what's called the quantum depolarizing channel, which is the quantum analog of the binary symmetric channel that you got introduced to earlier. Now, if you start with some arbitrary single qubit state that as input to this channel, and the channel is characterized by a single parameter epsilon, just like the alpha for a BSC, but this epsilon characterizes what happens to the state. So if you input psi, it leaves the state unchanged with probability 1 minus epsilon and applies X, Z, or Y Pauli errors with probability epsilon over 3. So these Pauli operators, X, Z, and Y, these bit flip, phase flip, and bit phase flip gates can also be thought of as errors introduced by this channel. So epsilon is a single parameter that tells you what happens on average to the output state. Okay, so that introduces Pauli matrices with these Pauli operators and how they can be thought of as errors. Now let's have a poll question. So here are your bit flip, phase flip, and bit phase flip operator definitions. So can you tell which of the following statements are true with respect to Y being a function of X and Z? Okay, looks like most of you are on the right track. Okay, I think we can end the poll there. Right, so C is the right answer. So we already saw that Y is a combination of X and Z. So if you have to make it precise, then Y is actually I times X times Z. And so you can check that for yourselves. All right, so let's move on. So now let's go to more than one qubit. So we saw one qubit and the Pauli operators on a single qubit. Let's say you have 3 qubits and the joint state is psi. Then you can apply different Pauli gates on different qubits, right? So, and then you have X, Z, and Y on these 3 qubits. Now, mathematically, the way we represent these operations is with a tensor product. So X tensor Z tensor Y implies that X is being applied to the first qubit, Z to the second, Y to the third. So there are different notations for this. We can drop the tensor product and put subscripts for these Pauli operators, and that tells you which operator acts on which qubit. And sometimes we even drop that and just concatenate this Pauli string, which assumes that these are indexed as 1, 2, 3, and X, Z, and Y are acting on the first, second, and third qubits. So that's how multi-qubit Pauli operators work. So there's a Pauli group mathematically defined on n qubits. It's basically all possible tensor products of the 4 single qubit Pauli operators, including the identity. So we saw the X, Z, and Y, but identity is also included. And then there can be a global phase, which is 1i, -1 or -i, where I is the imaginary unit, which is square root of -1. The Pauli group is the group generated by these operators acting on each qubit. And there are 4 to the n Hermitian Pauli operators, if you know what that means. And they form an orthogonal basis for all square 2 to the n by 2 to the n matrices. So when you do these tensor products, the size of the matrices grows exponentially. So each of these operators, X, Z, and Y, will be 2 by 2 matrices. But when you tensor product, it grows exponentially. And finally, this orthogonal basis with respect to the trace in a product, but this is not super important for this course. But these are important facts of the Pauli operators. Okay, so now let's look at the relationship between Pauli operators. So so let's say, so first when we do circuit notation, so this is quantum circuit notation. So time goes from left to right, which means you have the input state on the left, and then it goes through a sequence of gates to become an output state. Whereas when we write it as an equation, when you have a state psi, you go from right to left. So the first operation that's happening is X, and then the second operation is Z. Just like here, when you start from left, the first operation is X, the second operation is Z. And it turns out that X and Z on the same qubit anti-commute, which means if you change the order of X and Z, then you pick up a negative sign at the end. And so non-identity Pauli operators anti-commute. So that's a crucial concept that you want to remember for the rest of today, that XZ anti-commute, XY anti-commute, YZ anti-commute, only if they are on the same qubit. So X on the first qubit and Z on the second qubit will commute because they are totally different qubits, and the tensor product separates them. But on the same qubit, X and Z, or X and Y, or Z and Y anti-commute. So now let's go to 2 qubits. So you have some 2-qubit joint state, and you know that X and Z anti-commute, and they pick up 2 negative signs. But because you have one joint state at the end, the negative signs multiply to become a positive sign. And so the way to check this mathematically is using this property of the tensor product, that A tensor B times C tensor D is AC tensor BD. So if you do this with these operators here, so you have Z tensor Z times X tensor X, that's what is here. And then you can apply this property that becomes ZX tensor ZX and then ZX anti-commute. So you pick up the negative sign, but the negative sign multiplies to become a positive sign, and then you can write it separately as this tensor product. So this is just the circuit notation, and this would be the mathematical way of writing it. Okay, now let's take this. So we have two operators on two qubits that commute. X tensor X and Z tensor Z commute. So I'm dropping this tensor product notation to write it just as XX and ZZ. And if you multiply, you'll get minus YY. Remember, these are on two qubits. So this is X on the first qubit, X on second qubit, and so on. Now, this is what we call as a stabilizer group. The stabilizer group is basically a set of Pauli operators that commute. So here we have XX and ZZ commuting, but you can check that YY also commutes with these guys. And linear algebra tells us that if you have a bunch of matrices that commute, then you can simultaneously diagonalize them, which means that they have a common basis of eigenvectors in which they can be represented. So recall from linear algebra the concept of eigenvectors and eigenvalues. So all these matrices individually have eigenvectors and eigenvalues. But this fact tells you that when two operators commute, then both of them have the same set of eigenvectors, but they could have different eigenvalues. All right, so now let's use this fact to start making interesting things. So we have the stabilizer group here, and it turns out that because they commute, they have a common eigenbasis, and this common eigenbasis of these particular operators is famous. It's called the Bell basis. So here are four Bell states, each with different notation. Now, one thing to note here is that when I write 0, 0 inside a ket, this is actually ket 0 tensor ket 0. So this actually refers to ket 0 tensor ket 0 plus ket 1 tensor ket 1. I'm just dropping the tensor product just like I did for the Pauli operators. So you can write these four states, and you can actually verify that these are indeed eigenstates of these operators. So for example, I'm showing you an example here where I'm applying X tensor X on this state. And because of this property, when you apply X tensor X on this 2-qubit state, so the first X gets applied to the first qubit and the second X gets applied to the second qubit. And by linearity, the same thing happens with the second term. And you know that X flips 0 to 1 and 1 to 0. And so you see that you get back the same state. And therefore, the eigenvalue for this state is +1 with respect to the operator XX. And you can do this for all the other operators and all the other states. And once you have defined this common eigenbasis, now we can define a stabilizer code, which is basically the subspace spanned by all the eigenvectors of these operators that have a +1 eigenvalue. So instead of including all the four states, you are restricting yourself to only the eigenvectors that have a +1 eigenvalue, which in this case is only phi plus. You can check that phi plus has a +1 eigenvalue with XX, like here. You can do the same calculation with ZZ, and you will see that it still has a +1 eigenvalue. So in this case, you only get a one-dimensional subspace that is spanned by a single vector, which is phi plus. But the concept is the same. And now we're going to generalize shortly. The concept is the same. Now let's give you some practice. So here is all the facts that we just covered. And now I want you to compute the eigenvalues of the state psi minus, which is 0, 1 minus 1, 0 over square root of 2 with respect to XX and ZZ. So you can basically repeat a similar calculation and answer what the eigenvalues of the status are. Okay, maybe we can close the poll there. I think most of you got it right. Maybe there was some confusion between B and D, but if you calculate the eigenvalues, you will see that both the eigenvalues are -1, because when you do XX on 0, 1, -1, 0, the X will flip the 0 to 1 and the 1 to 0. So the terms will swap. And so you have to pull out a negative sign to get back to the same state. Therefore, that overall negative sign becomes the eigenvalue. So maybe just a little bit of more time and you can figure this out. Okay, but now we have seen the commutativity relations of Pauli operators and these eigenvalues of the common eigenbases. Now let's start making interesting codes. So we had this one-dimensional subspace when we asked that it be stabilized by both the operators. Now we are going to relax the constraint. I'm going to remove XX from being a stabilizer, and I'm only going to ask that ZZ is a stabilizer, which means I'm only looking for a subspace of vectors which are all +1 eigenvectors of Z tensor Z. So out of all these vectors, if you know where to look, you will see that these last two vectors will have a -1 eigenvalue for ZZ. And so those get removed, and you get a subspace that's spanned only by the first two vectors, phi plus and phi minus. And this becomes the code space in our case. And so you can actually encode one qubit, one logical qubit of information into these two qubits, which is spanned by phi plus and phi minus. Or if you change the basis, you can just write it as a linear combination of 0, 0, and 1, 1. So you have found a way to encode one logical qubit into two physical qubits. And this state, this two qubit state, is always a +1 eigenstate of ZZ, independent of what these coefficients are. So alpha and beta can be anything, but these will always be +1 eigenstates of ZZ. That's the crucial part, because alpha and beta is where your information is, and so you don't want the encoding to depend on the information. All right, so here is the quantum circuit way of forming the state. So you would start with your single logical qubit and then introduce an ancillary qubit in the 0 state. And if you do a CNOT and follow the rules of a CNOT, you will see that you end up preparing the encoded state that you want. Now, once you have encoded the state, we saw that you need to manipulate this logical information. But now you have encoded it into two qubits. So the only thing you can actually touch in the lab are these two qubits, not this logical qubit directly. And so you have to find a way to operate on these two qubits so that you do some computation on the logical qubit. And that's what these calculations are showing. So here, if I want to flip the logical qubit, I want to do an X. It turns out that the way to do it is by doing an XX on both physical qubits, and that does exactly the operation that you want. And so the logical X operator is actually the physical XX operation. And similarly, if you want to do a phase flip on the logical qubit, it turns out that you can apply a Z to either of the physical qubits, and that will change the sign to represent the logical flip. And so the logical Z is a physical Z on any of the two logical qubits. And then Y is a combination of X and Z. And so the logical Y is also a logical combination of the operators. And so this is what we call the logical Pauli operators. They help you to manipulate the logical information by only acting on the physical qubits. So hopefully that sinks in. So these logical Pauli operators play an important role, and they also determine the distance of the code. So they are quite important. So for any stabilizer code, you will have a stabilizer group that tells you the subspace that forms the code. And the subspace is defined as the +1 eigenspace of the operators in the group. And once you have identified the subspace, you find an encoding map encoding circuit that encodes the k logical qubits into n physical qubits. And then you identify the logical poly operators by identifying which physical operators do the logical X and logical Z on your logical qubits. And so that kind of sums up the most fundamental things of quantum error correction. So when we want to do arbitrary quantum computation, you have to synthesize all logical operators, which means you have to translate a universal set of quantum gates. And remember, our universal set had three things: Hadamard, T, and the control knot. So you have to do this translation not only for the poly operators, but you also have to do it for Hadamard, T, and C naught. Next poll question. So we have our 2,1 quantum error correcting code, and we have these logical operators. And remember, these are 2-qubit operators. So this is X tensor X, this is Z tensor I, this is I tensor Z. Now I want you to calculate if these logical operators commute between themselves and if they commute with the stabilizers. In the interest of time, let's close the poll. Yeah, I think most of you got pretty good. So maybe there was some confusion between B and C. So yes, it's true that X bar and Z bar anti-commute. As you can see, X on the first qubit and Z on the first qubit do anti-commute. Or if you check with the other one, X on the second qubit and Z on the second qubit anti-commute. But XX and ZZ already commute. We already checked that. And you can see that Z already commutes with Z. Therefore, the logical operators do commute with the stabilizers. And so the answer is C. So this is a key fact to remember. So a logical qubit is just like a physical qubit. X and Z on the same logical qubit will anti-commute, and X and Z on different logical qubits will commute. But all logical operators will commute with all stabilizers. Okay, let's proceed. So now we have seen how to encode, and we have seen this 2,1 code. And so we already saw that poly operators form an orthogonal basis. And this is actually the key fact why it suffices to only consider poly errors, because somehow if you have more complicated errors, you can write it as a combination of poly errors and then work your way through correcting them. So there is some caveats there. There is some important technicalities, which I'm not going into today. But the core fact is true that poly operators form bases, and so you can think of other errors as combinations of poly errors. And so the process of error correction is that an error happens on the state. In this example, an X error happens on the first qubit. So instead of 0, 0, and 1, 1, you have 1, 0, and 0, 1. You measure your stabilizer. You measure ZZ using a circuit that I'll show later. And so when you measure, you get the eigenvalue for the state. And then in this case, you can measure that the eigenvalue of this state with respect to ZZ is not +1. It's actually -1 because Z acting on 1 will produce a -1, and Z acting on this one will also produce a -1. So the eigenvalue for this state is -1 with respect to ZZ. And so this is called the syndrome, just like we saw for the classical error correction case. And using this -1 syndrome, your decoder estimates the error, which in this case could be the error that actually happened, or an equivalent choice would also be IX, because IX will also cause the same syndrome to be -1. But this will cause a logical error, as we'll see shortly. So here is the circuit. So after, say, the encoding, let's say an X error happened, it changes the state. When you measure the syndrome, here is what happens. So let's say you're applying ZZ to find the eigenvalue. Now an error already happened, and the error in this case is X on the first qubit. Now we know that ZZ and Xi anti-commute, and so you can reorder them with a minus sign outside. But ZZ acting on the state does nothing because ZZ is a stabilizer. And so ZZ acting on the code state just becomes the code state, and then Xi is your error. So overall, you have this eigenvalue equation that ZZ acting on the error state gives you -1 times the error state. And therefore, the error state is a -1 eigenvector of the stabilizer. And so that's what actually happens when an error happens. So the syndrome is basically the commutativity relation between the stabilizer and the error. And so that's what you take as the input. If you correctly decoded and your decoder predicted Xi to be the error, then the original error was Xi. And when you apply your correction, the E hat, which is the estimate from the decoder, you end up canceling the error and you go back to the original state. So you did the right thing. However, your decoder could have equivalently guessed IX to be the error because that has the same syndrome. It's indistinguishable. So if the decoder predicted IX as the error and you applied this as your correction, then the original error times the correction that you applied actually becomes a logical operator, XX, and therefore you have fundamentally changed the logical information. You have actually applied a logical error to the state. And this is what I mentioned earlier in the chat when Michele was presenting about classical error correction. Remember if you send 0, 0, 0 through the channel and the channel flips 2 bits, it became 0, 1, 1. And that's closer to 1, 1, 1. So your maximum likelihood decoder predicts 1, 1, 1. but that changed the logical information from 0 to 1. And this is exactly the quantum analog of that, where your decoder miscorrected the error and caused a logical error. Here is another poll question, just to make sure that what I said makes sense. So you have the code definition and the logical operators. Now, what is the syndrome for the error Zi? If we looked at the error Xi, what is the syndrome for the error Zi? And tell me if it's correctable. Okay, maybe let's close the poll. So I see that there could be some confusion here. So you were correct that the syndrome is +1, right? However, if the syndrome is +1, then the decoder assumes that everything is okay, right? So the syndrome is +1 is the ideal situation. If you don't measure a -1, the decoder doesn't know that something went wrong. Therefore, it doesn't do anything. So if the syndrome is +1, then it just estimates that the error is identity. So nothing happened. And so in this case, if you had a Z error on either qubit, because it commutes with your stabilizer, you will not see it in the syndrome. And therefore, any kind of Z error will not be correctable for this code. So only if the syndrome is -1 somewhere, that you try to correct. Otherwise, you just assume that everything was okay. So yeah, this is clearly just a trivial toy code that doesn't even correct a Z error. Now, we want to use all the knowledge we have about classical error correction to design quantum codes. So let's see how that connection works. So the main bridge to classical codes is this binary notation. So let's say we have a Pauli operator on, say, 3 qubits as an example. We have X on the first qubit, Z on the second qubit, Y on the third qubit. Now, our binary notation for A and B is going to be like this. So A represents the X component. So wherever you have an X, you put a 1. because y is a combination of x and z, you still put a 1 for y. But if you have a pure z, you put a 0. And b, as you might have guessed, is the z component. And so wherever you have a z or a y, you put a 1. Wherever you have an x, you put a 0. And so that's how you translate a tensor product of Pauli operators into a pair of binary vectors a and b using the x and z components. And once you have done this mapping, so this is not just a simple notation, it can be used mathematically to check commutativity. So here, for example, you have two Pauli operators, and you can write their binary notations. And you can already check if they commute, right? So because for commutativity, you just have to check in how many positions they anti-commute. So x and z anti-commutes, so that's a -1. Z and z commutes, so that's a +1. And y and x anti-commute, so that's a -1. So 2 times you get a -1, so overall you get a +1. Therefore, you already know that these two operators commute. Now, how do you check it using the binary notation? And here is the so-called symplectic inner product. So I'm going to define this as AB and this as CD. And the symplectic inner product tells you that you should take the inner product of the vectors A and D and the vectors B and C, and then sum them up modulo 2, meaning you're doing an XOR. If this sum is 0, then the operators commute. If it's 1, then they anti-commute. And the logic is simple. You're just trying to find in how many places an x in the first operator or a y, an x in the first operator intersects with a z. So each time you should get a -1. And similarly, whenever you have a z on the first operator and x on the second operator, you should still get a -1. And this is just counting the number of -1s modulo 2. That's all. So in this case, the way you would do these vector inner products would be like this. So you take the inner product of A with D and B with C. And so if you do those inner products and sum them modulo 2, you get 0. And so you concur that these two operators indeed commute. Okay, so now let's get some practice with that. So find the binary representations for these two Pauli operators, and then answer whether they commute or not by computing the symplectic inner product. An example is shown on the left. Okay, I think you get the idea. Let's close the poll there. Yeah, so B is the right answer. So XXX would be denoted as 111000 because the X component has all ones. And similarly for ZZI, the X component will be 0, but the Z component will be 110. And if you do the inner product, you can check that it will be 0 because they commute. Okay. Now once we have this binary notation, let's take our two stabilizers, ZZI and IZZ. Let's write their X and Z components. And then we can easily see that they commute because they're all Z operators and Z commutes with Z. And so now you can write a quantum parity check matrix where it has 2n columns. So remember, a classical parity check matrix has n minus k rows and n columns, like Michele introduced. In the quantum case, because you have this X and Z parts, you have twice the number of columns, but you still have n minus k rows. So you have two stabilizers here. And so I have 2 rows for the parity check matrix. And we split it into X part and a Z part. And because stabilizers must commute, it means that the symplectic inner product between any pair of rows must be 0. And that is represented by this equation here, which basically does the symplectic inner product between different pairs of rows. And so as long as a matrix satisfies this, you have a valid quantum parity check matrix. And we already saw that the syndrome is basically the commutativity relation of the error with the stabilizers. And therefore, given the symplectic inner product definition, the way you can compute the syndrome in software, if you know what the error is, and if you represent the error as C comma D, then you can just compute the symplectic inner product with each of the stabilizers, which can be done directly by this matrix vector computation. So HA is the X part, HB is the Z part, but D is the Z part of the error and C is the X part of the error. So you swap them and then you take the inner product modulo 2 and that will give you the syndrome. Of course, this syndrome is in the 0-1 domain, whereas in reality, they represent eigenvalues +1 and -1. So +1 is being mapped to 0 here and -1 is mapped to 1 here. So whenever you see a syndrome of 1, that corresponds to a -1 eigenvalue. And then that's what you feed into the decoder, and the decoder tries to figure out what the error could be. Okay, now let's go from these Bell states to GHZ states and to 3-qubit codes. So just like the Bell state, you can write a 3-qubit state called the GHZ state, where you have 000 + 111 or 000 - 111. And those have 3 stabilizers. Now, if you want to restrict yourself to only +1 eigenvalues, so you remove the XXX stabilizer and you only have these 2 stabilizers like we had in the previous slide. And then you get a 3-qubit code encoding 1 logical qubit, which is purely a generalization of the toy example we already looked at. So this is just to show that you can keep going. And in this case, you again have logical X and logical Z operators, very similar to what we did before. Now, one important thing I want to highlight here is that this is not the same as the classical repetition code, even though it looks very, very similar. So this is a linear combination of these 000 and 111 states, which is not the same as copying this logical qubit 3 times. So if you did the psi tensor psi tensor psi, if you just had 3 copies of psi, that will not give you a state like this. In fact, quantum mechanics prevents you from cloning quantum information. So you could not clone an arbitrary quantum state. And so this so-called quantum repetition code is not really a repetition code, but it is closely related with the classical repetition code. Okay. Now let's go back to syndrome measurement. So in software, if you know what the error is, then you can just use the stabilizers to compute the commutativity relation, and that gives you the syndrome, right? That's can all be done in software. But in practice, in reality, in the lab, if you initialize the quantum state, you have to make a measurement to figure out what the syndrome is. And here is how you would measure stabilizers to get the syndrome. So here you have two stabilizers, ZZI and IZZ. And let's say an error X happened here. Then the way you measure stabilizers is you do a C0 from the data qubit to the ancilla, initialized in the 0 state, and then you measure the ancilla in the Z basis. And this is all for Z-type stabilizers. If you have other X-type stabilizers, the circuit will change a little bit, but the concept is the same. So you have to couple your data qubits to an ancilla and measure the ancilla, and the measurement tells you whether the eigenvalue is +1 or -1. And the way you can check that this is exactly the commutativity relation is by doing the following. So if you have an X error on the first qubit here, and if you measure the syndrome, what happens is the X error propagates through the C0, and it actually flips the ancilla qubit. And by flipping the ancilla qubit, the Z measurement, instead of +1, will become a -1. So this is how errors propagate through the syndrome measurement circuit and flip the measurement. And with this, you can clearly see that the number of these errors that go through the C0s and flip the measurement has to be odd if the measurement is -1. And that's exactly the commutativity relation between the error and the support of the stabilizer. So here the stabilizer is supported only on the first two qubits, and you only have one qubit in error, and therefore you have an odd number of times that X propagates to the ancilla, which is why the syndrome is -1. Otherwise, the syndrome would have been +1. And so both of these do the same thing. Only thing to remember is that in practice, you would implement a circuit like this, but in software for simulations, you can directly compute the symplectic inner product of the error with the stabilizer. All right, so yeah, so once you've put it in the stabilizer matrix, quantum parity check matrix form, you can compute the syndrome by doing this math. Now you see, for the same reason, if you had a Z error here, you can check the properties of a C0, and the Z error would not propagate to the ancilla. So Z error would just zip by, and therefore the measurement will never be flipped, which is why the code cannot correct any Z-type error. Therefore, this brings us to the important definition of the minimum distance of a quantum code, of a stabilizer code. We define it as the minimum weight of an undetectable error, which is the same as saying that it's the minimum weight of a logical operator. So an undetectable error is exactly an error like this, the Z, which goes through the circuit without ever propagating to the ancilla and flipping a syndrome. Therefore, in this case, the distance is 1. And in this case, you can also see that Z acting on the first logical qubit is a logical operator. So logical operators and undetectable errors are the same thing. By definition, a logical operator changes your logical state, which means it maps a code state into a different code state, and therefore the syndrome will always be +1 if you applied a logical operator. Therefore, it is an undetectable error. So if the channel applies a logical operator, we are screwed. Okay, so that's the definition of the minimum distance of a code, and you can actually apply the same definition to a classical code. In the case of a classical code, a logical operator is actually a code word. So Michele already told you that the minimum distance is the minimum weight of a code word for a linear code, and that's the same as saying it's the minimum weight of a logical operator. Okay, so here is the next poll question. So we have two errors here, XIX and IXI. Can you compute the syndrome? You can either do the symplectic inner product, or you can directly do that by comparing Pauli operators, whichever way you find convenient. Okay, in the interest of time, let's stop the poll. Yeah, so looks like there was some confusion. So the stabilizers in this case are ZZI and IZZ, and your errors are XIX and IXI. So if you take the error XIX and you compare with ZZI. So for example, if I have ZZI and IZZ are my stabilizers. So you can see that if you compare XIX with ZZI, X and Z anti-commute, and then Z and I commute, and I and X commute. So therefore, XIX anti-commutes with ZZI, and that's a 1 in the binary sense, in the 0-1 domain. Similarly, XIX also anti-commutes with IZZ because this last X and the last Z anti-commute. So that will also be 1. And similarly for IXI, you will still get, because this middle X anti-commutes with this Z as well as this Z, and therefore the syndrome will still be +1. So the correct answer is A. But again, you can go back and try doing this calculation again. You will see that the first is the answer. Now, what happens if you replace these errors instead of XIX and IXI? What happens if you do ZIZ and IZI? So your stabilizers is Z type and your errors are also Z type. So then what's the syndrome? Okay, I think people get the point. So let's close the poll in the interest of time. Yeah, so it is correct that in this case, all the syndromes will be 0 because the error is Z-type and the stabilizers are also Z-type. So the error both the errors commute with both stabilizers, and so the option is D. So hopefully that was clear. Therefore, again, this code cannot correct any Z-type error, so we need to build more interesting codes, and that's what Peter Shor did in 1994. He came up with this beautiful 9-qubit code where he basically concatenated this 3-qubit code that we have been seeing now and the X-type version of that code. So he basically took this, one logical qubit, encoded it into the X-type version of this 3-qubit code, and then took each of those 3 qubits and encoded it into the Z-type version of the code. So he used both variations, the Z variation and the X variation of the code, and by concatenation, he was able to build this 9-qubit code and actually show that it has parameters 913, meaning it encodes 1 logical qubit into 9 physical qubits, but it has distance 3, which means d minus 1 or d minus 1 over 2 is 1, and therefore it can correct any error on 1 physical qubit. If there is an error on one of those 9 qubits, the code can correct it. And this was the first example of a quantum error correcting code. Before that, people were thinking that noise is a fundamental problem for quantum systems and it can never be corrected because it's continuous, it's unitary, and so on. But Shor beautifully showed that it is indeed possible to correct quantum errors by quantum error correction. So in this case, you have 9 minus 1, 8 stabilizers, n minus k. And in this case, it turns out that 6 of them are Z-type and 2 of them are X-type. Another way to visualize this code is this concatenation. So you first encode into the X-type code, and then you take each of those qubits and encode it into the Z-type code. And therefore, each row here represents 1 logical qubit of the X-type code. And then by concatenation, you get this 913 code. And so, and once Shor came up with this idea, that basically spawned the field of quantum error correction. And so for the past 3 decades, people have been constructing a lot of interesting codes. Okay, now let's see the quantum variation, the quantum version of the Hamming code that Michele showed you. So recall that the parity check matrix looked like this. Now we can make the so-called Steen code by taking the quantum parity check matrix to be of a block diagonal form, where you have one part which is purely X-type, the Z part is 0, and the bottom half is purely Z-type, and the X part is 0. And for both the X-type stabilizers and the Z-type stabilizers, you're using the same parity check matrix of the Hamming code. And therefore, these ones represent both X-type stabilizers and Z-type stabilizers. So the first row, for example, can be read as X1, X4, X6, X7. That will be the first row here. Or if you look at the first row in the bottom half, this can be read as Z1, Z4, Z6, Z7. Now you can check for commutativity. If you just do this commutativity symplectic inner product, you will get HH transpose, which you can check is 0. And in this case, the logical Pauli operators can just be defined as X on all qubits for the logical X and Z on all qubits for the logical Z. In fact, you can simplify these because multiplying logical operators by stabilizers doesn't do anything because stabilizers fix the state. So instead of applying a logical operator, you can apply a stabilizer and then a logical operator, and that doesn't do anything. So if you take these stabilizers, you can multiply the logical X operator by the stabilizer, and that cuts down the weight of the logical operator. So instead of acting on 7 qubits, now it only acts on 3 qubits, which is actually the distance of the code, which is 3. Remember that the distance of a quantum code is the minimum weight of an undetectable error or the minimum weight of a logical operator. And in this case, because you have cut down the weight of a logical operator from 7 to 3 by multiplying by a stabilizer, the minimum distance of the code is 3. Now, how do you decode this code? The way you compute the syndrome is if you have an error, which is represented as C, D, you do the symplectic inner product, you actually get 2 distinct syndromes. So because of this block diagonal form, you get a syndrome for X-type stabilizers and syndrome for Z-type stabilizers. Now you can use the syndrome for X-type stabilizers to find out the Z-type error, because remember, this X-type syndrome is calculated as H times D transpose, where D represents the Z part of the error. And so you use SX to find what D is, and you use SZ to find what C is. So you use the X-type syndrome to find the Z part of the error, and the Z-type syndrome to find the X part of the error. And therefore, because you can do this, you can decode the Steen code by just using the decoder for the Hamming code. But of course, if X and Z errors are not independent, if they're correlated, then these decoders need to talk to each other. And that gets a bit more complicated. But the idea is whenever you have a code whose quantum parity check matrix has this block diagonal form, then you can actually run two decoders separately, one for the X-type stabilizers to correct Z errors, and one for the Z-type stabilizers to correct X errors. And so recall the standard array that Michele showed you. You could potentially use this to decode the Hamming to the quantum Steen code by applying it once for the Z errors and once for the X errors. So here is another poll question. So consider the set of all poly errors that a code can correct using standard array decoding. Then tell me which of the following should be true. The key is you're given a set of errors that the code can correct. And so using that, let's see if you can figure out which of these is true. Okay, let's close the poll. Yeah, so that was expected. So this question was deliberate. So there was a confusion between B and C. So the answer is C. So for a classical code, it is true that if you had a set of errors that a given code can correct, then each error must have a unique syndrome, right? That's also almost by definition. However, quantum codes are more interesting because there can be two errors that are both correctable and belong to the set, and they could have the same syndrome. And when would that happen is if both of them differ by a stabilizer. So for example, if you had say an X error on, let's go back to our Steen code example. Right. So let's say you had an X error on the first qubit. Now an X error on the first qubit is actually equivalent. So let's actually do X error on the third qubit. So if you have an X error on the third qubit, you can multiply the error by a stabilizer, right? And so multiplying X3 by this stabilizer gives you x5, x6, x7, which is a 3-qubit error. But x1, x3, and x5, x6, x7 will have the same syndrome. You can go and check this for yourself because they only differ by stabilizer, and the stabilizer by definition commutes with all other stabilizers. So the stabilizer by itself will have 0 syndrome. Therefore, you can have two distinct error patterns that have the same syndrome and the same effect on the code. And therefore, that's the answer for that question, that not every correctable error needs to have a unique syndrome. As long as the two errors differ by only a stabilizer, they will have the same syndrome, and technically they are both correctable. So this is the degenerate part of a degenerate nature of a quantum code, where you can have many different errors corresponding to the same syndrome and having the same effect on the code. Okay, now let's formalize CSS codes, which is all the codes that look like the Steen code, with a slight generalization that this block diagonal form need not have the same matrix on both sides. You can have an HX matrix and an HZ matrix. As long as they commute, they're orthogonal to each other, it forms a valid quantum code. And this is what Michele was referring to earlier. When you have two parity check matrix and they're orthogonal to each other, technically they're belonging to dual spaces. And then when you compute the syndrome, you'll have an X syndrome and a Z syndrome, which you can correct to use to correct the Z error and X error. And logical operators will commute with the stabilizers, and that's what is given by these inner products. And the minimum distance is the minimum weight of a logical X or a logical Z, and K is n minus the rank of HX and rank of HZ. So that's the notion of CSS codes. So you can, if you have two classical codes with parity check matrices HX and HZ, and they're orthogonal to each other, great, you just formed your quantum stabilizer code. So all CSS codes are stabilizer codes, but not all stabilizer codes are CSS codes. Now there's a nice way to visualize these codes. So you can draw these ladders. So if you have two classical codes, CX and CZ, with these parameters, and you have their duals living inside the other. So these are subspaces. That's what this ladder means. So this 0 subspace lives inside the dual of CX, which lives inside CZ. So CX dual is a subcode of CZ. And so the X stabilizers come from the code words of CX dual, and the Z stabilizers come from the code words of CZ dual. And the logical X operators come from CZ minus CX dual, and the logical Z operators come from CX minus CZ dual. And then you can write down the sizes of the dimensions of these spaces. Now, if these two codes are classical LDPC codes, CX and CZ, while satisfying this dual containing constraint, then you just formed a quantum LDPC code. So the most famous quantum LDPC code is the surface code. The way it's defined is it's defined on a grid. So I'm giving you a 5x5 example. So all these circles represent data qubits, and all these squares represent stabilizers or quantum parity checks. So the red ones represent X-type stabilizers, and the blue squares represent Z-type stabilizers. And all of these stabilizers have weight 4, which means the Z-type stabilizer applies Z on this qubit, Z on this qubit, Z on this qubit, Z on this qubit, and the eigenvalue should be +1. And similarly, this X-type stabilizer applies X, 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 and the eigenvalue must be +1. And then the logical X operator spans a vertical line. So it applies X, 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 X. So it's weight 5, and therefore the distance of the code in this case is 5. And the logical Z spans a row, and it's also weight 5. And it meets the logical X exactly on 1 qubit, and therefore they anti-commute as it's required. And you can check that the logical X and logical Z commute with all the stabilizers. So if you take if you take this Z-type check, which applies Z, 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 Z. It intersects the logical X exactly on 2 qubits. So you have an X and Z anti-commuting here and an X and Z anti-commuting here, but they happen twice. And so overall, this logical X operator commutes with this Z-type stabilizer. And you can do this check for everywhere. So it's a valid code and it's distance 5. And it is part of a family of codes which all encode a single logical qubit. They have distance L. Here L is 5. L is just the length of the grid. And the number of physical qubits you can count will be order of L squared. Now, what happens when you have errors? Right? So let's say you have errors here. So these circled qubits have errors. So this is a Z-type error, and this is an X-type error. So the X-type error flags Z-type stabilizers. So this Z-type stabilizer anti-commutes with this X error. And so you have a -1 syndrome here. And similarly, this Z-type stabilizer anti-commutes as well. So you get a -1 syndrome. So you see that whenever you have an error, it will flag 2 stabilizers if it's in the middle. If it's in the boundary, it will flag exactly 1 stabilizer. Similarly here, if it's in the middle, you have this chain where the endpoints of the chain will be -1 syndromes. But in the middle, you will have +1 syndrome. So these two won't be flagged because you have 2 X-type errors on a Z-type stabilizer, and so they commute. Now let's see how error correction works. So we run the so-called minimum weight perfect matching algorithm. The way it works is first it introduces these virtual checks for doing matching on a graph. Now we are going to form a new graph. So this is the code graph. Now let's look at these Z-type errors using X-type stabilizers, and we are going to form this X syndrome graph. So we have this X syndrome here that's flagged, and this X syndrome here that's flagged. Now I'm forming this syndrome graph where I'm drawing edges between the X syndromes that are flagged, and the weight of the edge is the minimum, the least length path between that connects the 2 X checks. So here I have the path goes through data qubits. So you have 1, 2, 3, 4, 5, 6 data qubits that connect these 2 X-type stabilizers. So if all these 6 data qubits were in error, then the syndrome will exactly look like this. It will look like -1 here and -1 there. And that's the reason for the 6. And then you also have these virtual checks to account for these boundary events. And so when you draw an edge from the real check to a virtual check, the weight is just the number of data qubits that need to be flipped to cause on exactly that real check to be flagged. And so that's how you form this syndrome graph. And then you run this minimum weight perfect matching algorithm, which is a well-known algorithm in computer science. So it basically tries to match the nodes in this graph such that each node is exactly matched to one other node. So here, instead of these multiple edges, you will have exactly one match. And in this case, it turns out that the best matching to find, which minimizes the sum of the edge weights, is this matching. So the edge weight is 3. For any other matching, the sum of the edge weights will be higher. But this is okay because the error was indeed on this qubit, and the algorithm matched this check to this virtual check, which means it's saying that this qubit is an error. And so if you go back and apply the same error, the error will vanish. Great. However, this is a problem because the true error was 3 qubits flipped on the left side, but the algorithm matched the check to the virtual check on the right side, indicating that the correction, the estimated error, is on these 2 qubits. So if the actual error is this, and you apply a correction on these 2 qubits, together you just formed a logical operator, and therefore you caused a logical error. So that's how error correction works on the surface code. So error events usually flag a pair of syndromes unless they're boundary events. and you run this matching algorithm to find what the error was, and you apply a suitable correction. And now we get back to this curve that I showed you in my first slide of this section. So if you just do this simulation that I just explained, if you run this matching algorithm for these different distance codes and you compute the time to failure, you will find this threshold, which is about 15% on the depolarizing channel. So this 15% is the epsilon parameter for the depolarizing channel that we introduced earlier. And you can go to this paper if you want to learn more about how to set up the simulation and go into some details. But that's basically how quantum error correction works. Okay, quick poll question. Let's make this fast so that we can wrap up this section. So the question is about a logical error. Okay, let's close the poll. Okay, so the answer would have been B if the question was when the decoder succeeds, right? Because the true error times the error estimate, which is the correction you're applying, should multiply to a stabilizer so that the overall effect of the error and the correction is applying a stabilizer to the state, which fixes the state. So it leaves the state unchanged. But the question is about a logical error, which means you should, if you take the original error, and if the error estimate is different and they multiply to form a logical operator, that's exactly when you have miscorrected the error and you have caused a logical error on the state. So you have inadvertently changed the logical state and your error correction failed. All right, so let me just briefly tell you about some good quantum LDPC codes, and then we'll wrap up this section. So the hypergraph product code is one of the first known family or construction of quantum LDPC codes. So without going into details, the way it works is you can take any two classical codes. So for the CSS construction, we needed two classical codes which commute, which are orthogonal to each other. So here it gives you this construction using tensor products, where you can take any two classical codes with parity check matrix HA and HB, and if you plug it into this construction, it gives you HX and HZ such that this condition is satisfied. And so you have two types of qubits, these orange qubits and these green qubits. And the surface code is actually an example of that. You can take two repetition codes and you can do this hypergraph product, and you will get these orange type data qubits and the green type data qubits. And then you have the blue type and red type parity checks, which are the stabilizers. So this hypergraph product code has given many interesting code families, and these can all be decoded using this belief propagation algorithm or the bit flipping algorithm that Michele told you. These are all message passing type algorithms. And so some remarks on decoding. So unlike classical error correction, where you can have a received vector and you can look at the bit values or the and then decode. In the quantum case, you don't have received vectors. You have to decode based on only the syndrome. There is no received vector. Now, if you have no XZ correlations in the errors, you can run two independent decoders for CSS codes. But if you have a depolarizing channel which has a Y error, which is a combination of X and Z, that is correlation, then you have to do something more clever. And then you can plot physical error rates versus this logical error rates, and you get curves like this. And the performance depends on the scheduling of the messages. You still have this error floor phenomenon where the logical error rate doesn't keep going to 0 as the physical error rate becomes lower and lower. It actually saturates. And then degeneracy that we have already seen is actually a boon to quantum error correction, but it has to be carefully leveraged in the decoding strategy. So the last few years has seen an explosion of work in constructing good quantum LDPC codes, and we have optimal quantum LDPC codes constructed today. So that was a long-standing open question, but this paper of Pantalev and Kalashev gave us optimal constructions. And now we are working on building good decoders, finding how to do computation on these codes, and then figuring out how to map these to hardware and actually build these quantum computers. So to summarize, these surface codes are called topological codes. They've been studied for a long time, whereas these optimal quantum LDPC codes are quite recent. And so some of these aspects need much more research. And it remains to be seen if we can kind of build scalable quantum computers with low overhead. Okay, the final poll question before we close this section. Okay, I think people get the idea. We can close the poll. Yeah, it is indeed true that all the above are true, that you have these sparse parity checks. And remember, the size of the weight of the stabilizer determines how many CNOTs you have to make for the stabilizer measurements. And so you want sparsity because the smaller the weight, the more efficient the circuits are. Okay, so in summary, so we have these code parameters n, k, and d, just like classical codes. You encode k logical qubits into n physical qubits, and the minimum distance is the minimum weight of a logical operator or an undetectable error. We looked at the bit flip code example where you have this encoding, and then you do syndrome measurement by doing these CNOTs. And so you want the number of CNOTs to be small so that the CNOTs themselves don't cause more errors. Which is why you like sparse codes or LDPC codes. And so you compute the measurement and then send it to a decoder, and then the decoder tells you what the error estimate is. And we typically use these fast message passing algorithms on LDPC codes. That completes this section. So I know it was pretty long, but hopefully it was useful and informative. Let's again take a few minutes break and come back in 5 minutes to start the last part. that CG will tell you about. Thank you.
Okay, so hello everyone. So let's start. After the first part, classical error correction by Michele, and the second part, quantum error correction by Professor Goswami, I believe you now have a basic understanding of quantum error correction concepts. For my part, let's explore how to apply these concepts in real-world situations. Let's start with a brief overview of a 311-bit flip code. At the beginning, we have a quantum state. After encoding, we can get the coded state. If an error occurs, we can use the syndrome measurement to get the syndrome for error. Generally, if there's no error, the same quantum circuit can be used to get the sign for stabilizers. From now on, we will focus on using the biostate as a tool to demonstrate quantum error correction applications. In fact, it is similar to the 301 code, but we concentrate on just 2 qubits. The key difference is that we can send these two parts to different locations to create a biostate, a biopair. Consider a pair between points A and B. The measurement will break up the pairs. However, because the pair is entangled, measuring one part of the pair will cause to deterministic measurement result on the other side. For instance, if we have a biopair, but if we have a biostate of 0, 0 plus 1, 1, and A measures a pair of the biostate on X and gets plus 1, we can confidently say that if B measures his part on X, he will also get plus 1. Here, the plus state simply indicates a measurement on X resulting in plus 1. Interestingly, measuring just one part is sufficient. The other part will automatically align to the same result without needing actual measurement. And these two situations are equivalent. In this part, since we are focusing on application rather than the core mathematics or quantum mechanics, I feel there's a very interesting way to introduce it. At the beginning, let us use some symbols to represent our learning so far, as they can be extremely helpful in grasping the key ideas of error correction in quantum networks. At first, uncoded state without errors will be represented by dots, and those with errors by stars. We will use squares to represent stabilizer generators. Imagine this is a box, and then placing an uncoded state inside, turn it into a coded state without error, symbolizing the box's protective nature. A square with its corner cut off represents a coded state with error. Similarly, small squares will denote the sign for stabilizers, and their corner-lit version will represent the symbol with for the error. These cut corners mean estimated error. At the same time, we will use the different arrows to represent the classical channel without error, the quantum channel without error, and the quantum channel with error, respectively. Next, these boxes will denote syndrome measurement, decoder, and correctors. And then the wave lines with dots mean biostate, and the wave lines represent the biopair without error, and the dashed line for those with errors, and the double lines will represent equality. Now, let's apply these symbols to some previously discussed concepts. First, given stabilizer generator of stabilizers and a coded state with error, using the measurement, we can get the syndrome for error. Second, given stabilizers, the sign for stabilizers, and the syndrome for errors, using a decoder, we can get estimated error. Finally, if the estimated error matches the actual error, using the correct quantum circuit, we can correct it to get the coded state without error. Okay, let's start. At the beginning, let us imagine a quantum networks. Here, we will have a bunch of quantum nodes, which could be computers, sensors, or whatever. To simplify, we will discuss a network with just two nodes and one directional communication. This means we are transmitting a quantum state with information from one node to another through a quantum channel. If the distance is short, there is a very low probability of getting an error. However, as distance increases, channel noise intensifies, reducing fidelity and eventually leading to channel failure. Later, if we also want to do some quantum network operations, it will make the channel fail very quick. Therefore, we need a way to correct errors and increase the stability of quantum bits in the network. This process is known as quantum error correction. Let's go deeper. We will name our node Alice and Bob. If Alice sends an uncoded state through a noise quantum channel, Bob cannot correct his errors because the state information is already lost. Thus, encoding is essential. Therefore, once Alice has an uncoded state, she can select a series of stabilizers. After encoding, she can get the coded state and sign for stabilizers. And then Alice sends the stabilizer generators and the signs to Bob through a classical channel, which is assumed to have no error inside. Next, Alice sends the coded state to the Bob through a noisy quantum channel. Upon receiving the coded state with errors and the stabilizer generators from Alice, Bob can use the measurement quantum circuit to get the syndrome for error. Using the stabilizers, signs, and the syndrome for error. After decoding, Bob can get the estimated error. Finally, if the estimated error matches the actual error, Bob can correct it by using a quantum circuit to get the coded state without error. Finally, the coded state can successfully transfer from Alice to Bob. Throughout this process, most noise in the quantum circuit could be ignored, except for the decoder, which is the core point for quantum error correction. A quick summary. The sending order is not important, actually. Alice could first send the quantum state through a noisy quantum channel, followed by the stabilizer and signs through the classical channel. And then Bob can use the decoder to estimate error and to correct it to receive the coded state. Now, this is the first poll question. What is the primary purpose of quantum error correction in quantum networks?
I think the poll is closed, CG.
Oh, okay. Oh, I see. All right, that's correct. The answer is D. The quantum error correction in quantum networks means correct errors caused by noise and operations in the quantum net channels or quantum networks to improve the stability of quantum bits. Okay. As I mentioned, the decoder is the core quantum error correction. Ideally, it should work perfectly. However, there are two main problems that could lead to decoder failure, consequently causing the entire channel to fail. The first problem is long distance. As distance increases, the coded state accumulates more errors, leading to what we call the decay problem. When the number of errors is larger than the limit that the decoder can correct, it will fail. A typical solution is using repeaters. Between Alice and Bob, we can introduce a node called a repeater. Depending on the situation, the number of repeaters can be different, but we will focus on a single repeater scenario. First, Alice sends the coded state and the classical information to the repeater, which can use decoder to estimate error and correct it. And then the repeater forwards the corrected coded state and classical information to Bob. Finally, Bob can use his decoder to estimate error and correct it again, successfully transferring the coded state from Alice to Bob. In summary, because long distance could trigger the decoder failure, we can use repeater to reduce the error correcting pressure on a single decoder by shortening the distance. Now, our second poll question: what's the primary purpose of quantum repeater? Okay, yes, the answer is B. The goal for the repeater is to solve the decay problem. The rest of them are not the primary purpose. Okay. So now, the second problem arises even when sufficient distance. Environmental factors can cause too many errors, leading to decoder failure. This is a problem we cannot fully solve. Thus, we need an alternative approach where decoder failure doesn't cause quantum channel failure. One solution is to perform decoding earlier than the actual communications. To understand this, let's revisit the properties of the Bell state. At the beginning, Alice prepares a Bell state and sends part of it to Bob through a quantum channel. Here, we assume the quantum channel is perfect, and then the parts at Alice and Bob form a Bell pair. The mathematical form is in below. I may not go deeper this part. Okay, now, importantly, if we have n Bell pairs and a series stabilizer generators, after mirroring, we can get k-coded Bell pairs. And the stabilizer size. The stabilizer measurement doesn't break up the Bell pairs, and the pairs are protected by the stabilizer. Furthermore, if we only do measurement in Alice part, the Bob part will also follow the rules. And these two situations are equivalent. Based on this property, we can go to the next point called teleportation. At the beginning, Alice and Bob generate several Bell pairs, and then Alice wants to send a coded quantum state to Bob. After the operations and measurement, between the coded state and one of the coded Bell pair, Alice can get classical information that shows the difference between the coded state and the coded Bell pair. And then Alice needs only to send this classical information to Bob. Based on this information, Bob can transform another part of coded Bell pair into the coded state that Alice wants to send. Be careful, we never observe what the coded state is, but the differences between the coded state and one of the coded Bell pair. During this process, we will use Bell pair plus classical information to transform the quantum state, and the information is in the classical channel, but not the quantum channel. This idea gives us a new way to solve the decoder field problem. First, in a noisy quantum channel, we establish an imperfect Bell pair. Then, as with quantum error correction, Alice sends the stabilizers and their signs to Bob through a classical channel. Bob uses the decoder to estimate and correct errors. If the decoder fails, the attempt is discarded. However, if successful, the Bell pair is retained. This process can improve the purity of the quantum state. When Alice is ready to transfer coded state, we only need to send the relevant classical information to Bob. Using this information and the Bell pair, Bob can retrieve the coded state that Alice wants to send. In this part, because we need to do many times before the actual communication, and we only keep the successful part, we call it the distillation. A quick summary. In real-time communications, if there are too many errors, then the decoder will fail. Because of this, we first use error correction before the actual communication to improve the purity of Bell state. And then for the real-time communication, we use this good Bell state to do interpretation of the actual data. Now, for our third poll question, what's the primary purpose of quantum distillation? Okay. Just a little bit, let me see. Okay. So actually the answer is C. The goal for distillation is to improve the purity of the quantum states. The rest of them are not the primary purpose. It is a purpose, but not the primary one. So next, let us go through how to do the distillation based on error correction. Directly creating a Bell pair between Alice and Bob through a noisy quantum channel won't allow Bob to correct errors, leading to failure. Thus, we'll apply quantum error correction. Starting with unbound states and stabilizers. After encoding, Edison can get K-coded Bell pairs and signs. Because we use a Bell state here, the encoder could be implemented by stabilizer measurement on Bell state. And then Alice can send the stabilizer generators and signs to Bob through a classical channel. Subsequently, Alice sends part of the coded Bell pair to Bob through a noisy quantum channel and keep another one. Upon receiving the other part of coded Bell pair with air and the stabilizer generators, after a measurement quantum circuit, Bob can get the syndrome for air. Using stabilizers, signs, and the syndrome for air. After decoding, Bob can get the estimated air. If the estimated air matches the actual air, Bob can correct it using a quantum circuit to get the coded state without air. Finally, they can form perfectly coded Bell pairs between Alice and Bob. In the end, let us sum it up. First, quantum error correction. That means, based on the classical information that includes the stabilizers and signs for stabilizer plus the quantum state, we can correct this error in the noise quantum channel. Second, teleportation. That means, based on the classical information that includes the differences between the coded state and the coded Bell pair plus a perfect Bell pair, we can transfer the quantum coded state by using classical information. Third, detailation. That means, based on the classical information that includes stabilizers and the sign for stabilizers, plus the imperfect Bell pair, we can correct the error in the noise quantum channel. We can do this one again and again to avoid quantum channel's failure. Okay, so that concludes our discussion for this part. Thank you. And any questions?
Thank you, CG, for the last part on how to apply error correction for entanglement distillation and quantum repeaters in quantum networking. So that pretty much concludes the course. So just to recap, we started with classical error correction, some fundamental concepts that Michele introduced, and then we transitioned into basics of quantum information, and we saw how quantum error correction works, and we saw how it can use classical codes to build quantum codes. And we also saw quantum LDPC codes and their uses. We saw the surface code example in detail. And finally, we saw this in this last section, how we can use this mathematical technique to solve these long distance decay problem, as well as the problem of real-time failure of links. So there are many resources. If you want to continue learning about quantum error correction, the standard textbook in the field is called Quantum Computation and Quantum Information by Nielsen and Zhuang. That's the standard textbook that many people use. I'll put it in the chat here. But there are also other resources. So Daniel Gottesman has recently started writing a textbook on quantum error correction, and he has released half the textbook so far. If you Google, I think you should be able to find it. If not, feel free to send me an email and I'll send you the link. But I think that's an excellent and comprehensive resource. There's also a book called Quantum Error Correction, edited by so many people have written different chapters. It's edited by Daniel Lidar and Todd Brun. That's also an excellent resource. So these are some great resources to learn more about quantum error correction, but I also encourage you to follow the research. If you're from a research background, you can also see papers on this topic on archive. But yeah, happy to answer any questions. Feel free to contact me. I think the email's in the slides, but I'll also put it in the chat. But thank you for joining and thank you for registering. Hopefully the course was useful. And Suchi, if you could go to the last slide, please do respond to the course survey and give us some feedback if you found the course helpful. That would be very useful for us to know for the next time. I can stay for 5 or 4 more minutes if anybody has any questions.
Wonderful. Thank you guys for your time. Yes, please take the course evaluation survey. And then we'll be following up with the slides and a recording of the course in the coming days. And yeah, if you guys want to stick around for a few more minutes to answer any questions, we'll give it a couple more minutes.
Yeah. Maybe I'll answer this live. Yeah, so great question about non-poly errors. So yes, so there is this representation of channels called the Krauss operator representation. And so that's the most fundamental or most general way in which you can represent a quantum channel. So noise is generally represented using this Krauss representation. Now, because poly operators are form a basis, you can take the Krauss operators for any channel and write them as linear combinations of poly operators. And then under some assumptions, you can show that if you can correct a set of poly operators, then you can also correct any channel whose Krauss operators are linear combinations of the poly operators that you can correct. So that's actually how quantum error correction generalizes. So if you go to one of these textbooks, the main theorem of quantum error correction shows you that you can discretize the set of errors that you need to correct. And so if you can correct poly operators on up to say 3 qubits, then you can technically correct any linear combinations of those poly errors as Krauss operators. Now, people have looked at specific channels like the amplitude damping channel. So you have to change the kind of the theoretical approach of quantum error correction depending on the specifics of the channel. But overall, the idea is similar. That's maybe what I'll say for now. But yeah, I think if you look at papers that specifically look at these non-poly channels, they will tell you how things change. Any other questions?
Okay, we'll go ahead and end the webinar now then. Thank you guys so much for your time. and have a good rest of your day.
You too. Thanks, Priya.